In this video, we are going to talk about the basic algorithms for searching and sorting. Let's start with bubble sort. The way that bubble sort works is by iterating through the array and swapping elements on the go. We may need multiple iterations on the array to have it fully sorted. Here is an example. So we will have two pointers, one on the first element and one on the second element. We are going to compare the value in those two indexes. And as we can see here, 4 is bigger than 2, so we swap. Then we will increment. We still have two pointers. And in this case, we see that those two elements are in the right order, so we increment. Same, still in the right order, we increment our pointers, still in the right order, and here we are. We can see that 26 is smaller than 41, so we swap. And then we increment our pointers, right order, we increment, and we see that 44 is smaller than 64, so we swap. And we finished our first iteration. We can still see that our array is not fully sorted. So we are going through a second iteration. And same, we are going to look at the two first elements. They are in the right order. We increment, still in the right order, increment, still in the right order. And here we are. We have 26 that is smaller than 34. So we swap. And then we increment our pointers. We still have everything in the right order, increment right order, increment right order, and we finished our second iteration. Now we can see that our array is actually sorted, but the algorithm doesn't know that the array is sorted. So we still need to go through a third iteration to verify that. And we are going through everything. Everything looks perfect. And here we are, we finished. The complexity of bubble sort is O of n squared. And the space complexity is constant because we are not using anything else than the original array. Now let's see the selection sort. The selection sort works by having a pointer on the first element of the array. Then we search for the smallest element in the array and swap. Then we increment the pointer, look at the second smallest element, swap, and so on. Here is an example. So in our first iteration, we are going to have the pointer pointing to the first element. And then we are going to search through the array to look for the smallest element. And we can see that the smallest element is 2. So we swap them. Then we are going to increment our pointer in our second iteration. We are going to look for the smallest element in the array, which is 4. And we can see that we don't need to do anything. So we increment our pointer. Same here, we look for the smallest, which is 12. So there is nothing to do. And now we increment, we look for the smallest in the rest of the array, and we can find the 26. So we swap. We increment our pointer, we look for the smallest, we found 34, we swap. We increment our pointer, look in our the rest of the array, but the smallest is 41, so we continue. And then we can see that also we increment, and then we can see that the smallest is 44, we swap. And then we increment, and that's the last element. The selection sort complexity is also n squared. The space complexity is constant because we are not using anything else than the original array. Next, we have merge sort. And the way that merge sort works is by dividing the array in halves, and then each half is split in half, and so on, until we have only one element, each element being isolated. Then we sort each half and we merge them back together. So here we have an example. What we're doing is that we divide the array in two, and then we divide each subsection in two, and we divide again the subsection in two. And then we merge them back. We sort them and we merge them. And then we merge again the subsections 2 by 2. We sort them and we merge them. And then we once again sort them and merge. The merge sort time complexity is n log of n. And the space complexity is O of n, since we actually need additional space to save the partitions. Finally, we have quicksort, which is a divide and conquer algorithm. It picks an element as a pivot and partitions the given array around the picked pivot. We can pick any element as a pivot. So let's see an example. So what we're doing with quicksort is that we choose pivot. And here we choose the last element to be our pivot. So then what we are doing is that we move everything that is bigger than our pivot on the right side, and we keep everything else on the left side. Here we have only 64 being bigger than 44. So we move it on the right side. Then we are looking at the partitions separately. So let's look at this first partition. We choose still the pivot to be the last element of our partition, but here we have only one element, so there isn't anything to do. In the opposite side, which is the left side, we are also choosing the last element to be our pivot, which is 26. So we are going to move everything that is bigger than 26 on the right side. And we are going to keep everything between 26 and 44. So here we had 34 and 41 being bigger than 26. So they are going to be between 26 and 44. Then we have two new partitions. We're going to do the same. We're going to use the last element as our pivot. We're going to look at the right side first. And we chose 41 to be our pivot. Here, there isn't anything that is bigger than 41, so there isn't anything to do. On the other side, we have 12 being our pivot. Once again, we have nothing bigger than 12. So we are going to choose a new pivot. On the right side, the new pivot will be 34. But since it's the only element left, we are not going to do anything. On the left side, we can see that 4 is bigger than 2, so we are going to swap. And here we are. We have our array being sorted. The time complexity of this is n log n. And since we are not using any additional space, the space complexity will be constant. Although the worst case complexity of quicksort is n squared, which is more than many other sorting algorithms like merge sort and heap sort, quicksort is faster in practice because its inner loop, it can be efficiently implemented on most architectures and in most real-world data. Quicksort can be implemented differently by changing the choice of the pivot so that the worst case rarely occurs for a given type of data. So we are considering the complexity as n log n.